Good morning, everybody. I think we should start the webinar of today, which I think is very interesting. Artificial intelligence in mobile applications. We have here our fabulous guest speaker, Alexandra Dobrescu, which is an alumni of our faculty, and I will give the floor to her. Please, Alexandra, you may start your webinar. And thank you for being with us today.
Thank you so much for this fabulous introduction. It's a pleasure and honor to be here today. Probably I should I share my screen? I'm not sure if I should also share my camera. I'm a human, not a robot.
It would be nice. It would be nice.
Okay, just to be sure that I'm not a bot yet. Yeah, let's see how it goes. My favorite question is, can you hear me well? And also, second question, can you see my screen?
Yes and yes.
Great. Let's go full screen. So today we are going to talk about AI in mobile apps. It's a webinar. And yes, I'm Alexandra. And for today, I envisioned 8 chapters. Even though the world was built upon 7 days, we will have 8 steps. Probably the 8th step, the last step, the know-how is the most important. But to arrive to the know-how, we are going to start with the AI domain, that's the title, and pass through all these steps: the computer vision, the architectures, transformers, what's CLIP, quantization theory, and hopefully the mobile apps. So let's get started with the AI domain. So what is AI? And right now I'm thinking of that meme with AI. So I wanted to start with what is AI and how I like to look at it, and how I'm encouraging you to look at it. So AI, it's a discipline like physics. And more specifically, it's a branch of computer science. And what it does, it creates intelligent agents. So what are intelligent agents? They are systems that can do 3 things. They can reason. What does it mean? It means that we have a logical deduction and we can perform some inference to reach some conclusions, or even more importantly, make decisions. And practical applications, a practical application that you know about are the chatbots, the intelligent chatbots. So second step is learning. They can improve their performance over time by learning from data and experiences. And I'm thinking about autonomous vehicles that can learn from visual samples. Where is the road? What are some obstacles? Where are the people crossing the road? And many, many other applications. All these systems learn. And third step, they can act autonomously. So they can execute actions or, of course, make decisions without human intervention. And here, I like to give the third example. Those are the smart home systems. And with all their applications, the smart fridge, the coffee machine that prepares you coffee today during the lecture. And a definition that I also like is this one: AI is the theory and development of computer systems that are able to perform tasks normally requiring human intelligence. So the question that I also like is, what is the difference between AI and ML? ML, of course, comes from machine learning. So ML is a subfield. So the AI encapsulates the melee domain. And what is melee is a program or a system that allows us to train a model from some input data. And furthermore, this trained model can make useful predictions from new and unseen data. So to encapsulate all this theory, let's say, melee gives us the ability to learn without explicit programming. And of course, this third slide, it's linked to this slide. And now that somehow we established a small introduction for the AI domain, let's pass to computer vision and arrive to convolutional neural networks. But we cannot do this without looking back into the past, right? So how it started? Of course, with an inspiration from neuroscience that is still present today. On the left, it's represented a really nice experiment. I'm giving you here a link to the video. It was performed in the 79 years with this really nice cat, or multiple cats, I'm not sure about it, that was supposed to have an electrode inserted in her brain. And see during this experiment if, while looking at various stimulus, the stimulus were some type of traces, lines. The researcher wanted to see if the brain responds to this stimulus, like if the output will be an electrical signal. What was the scope of the experiment was to see if our brain has a link with the visual cortex, right? And why I'm talking about the present time? Well, a very concrete and industrial application that it's all over the news is the Neuralink experiment. But what I want you to show you is like the cats did it before it was cool, and it started in the 70s. That was the inspiration. So after the output of this scientific experiment, where we agreed that we have some visual signals that we can perceive with our brain, the researchers also wanted to see if we can bring a mathematical representation out of the neurons. And it started with a perceptron. It's another keyword for you. The perceptron, which is similar to the biological neuron, is represented in this figure. And what it does, by its rule, we have some input data I mentioned earlier that is somehow summed up with some certain weights and biases. And we envision to have an output to fire the neuron if this one passes through a certain signal, exactly how we do when we look at the natural neuron or to our dear cats. But what's the problem with this small perceptron? Well, it cannot go through complex tasks. It's not enough to have a single perceptron to make a complex decision. You remember that I said before, or 2 minutes, 3 minutes ago, that we want to make decision. We want to build complex stuff. So what we actually do, we come with more complex systems like this one represented here to perform certain tasks. And here we have another important term, the NNNs. What are these? Those are the artificial neural networks, and they extend the work by coming up with multiple perceptions combined and performing some type of classification, regression, whatever. And in essence, they are multiple layers of perceptions or neurons that allow us to come with a decision. But how it started? It started very, very, very simple. We are still in the computer vision space. This is the face detection task. It was again an experiment in which the researchers were identifying faces from certain images. As you can see, it's very fast. They were having like 15 frames per second using very standard Intel Pentium third. And compared with the very powerful and known deep face model, this one, their algorithm, has only 50K parameters and achieves high precision and recall, and is still employed in low computational scenarios. And what it does, it uses some very basic filters that are represented over here with black and white. And they are used to see if we can detect some eyebrows, noses, maybe lips, but it's not the case over here. Why I'm giving you this example? Because we remember the goal of today's webinar. We want to go to mobiles, and I think you know about mobiles. They are not very high computational, let's say. Again, here we don't learn anything. It's just a simple algorithm still used today that allows us to do face detection. And now let's see how the convolutional neural networks appeared. Well, in 1908, Jan LeCun, or our dear godfather in the AI domain, came up with this architecture, LeNet. He bring the idea of representing an image as a matrix, and furthermore, applying to this image multiple filters, such as, in the end, we are able to extract features. Features is another keyword. As you can see, as far as we go from left to right in this architecture, we go deeper. So we perform multiple matrix multiplication that can be parallelized to extract this feature, such as, in the end, we arrive to our output. As you can see here, our output is 10. This means that we want, in the end, to flatten our complex features extracted to make predictions, and 10 shows us the number of predictions that we want to do. And I'm sure probably you are familiar with this paper. Here it was the case of predicting the handwritten digits, which are from 1 to 9, well, from 1 to 10. But what happened? Actually, years later, when the GPUs were starting to take off, everything changed, and other researchers were able to come with more complex architectures and perform more complex computations. I want you to know that, like, the key of this AI domain, or understanding and developing application, is also linked to understanding architectures and how can we further use them. So we had these architectures. We had also the powerful GPUs, but we didn't have like data set. And data set, it's another keyword. In 2012, the researchers, other researchers, Stanford teachers, and other volunteers started collecting 1.4 million data, and they manually grouped them in 1K object classes. And why this was important? Because we were able to do an evaluation. We were able to see how a machine performs compared to a human. And as you can see here in this wonderful year, everything changed because we passed from traditional task to more convolutional neural network task, more learnable task. Remember that here we had face detection, nothing learned. But once we were able to have a data set of evaluation, everything changed. And I'm giving you this slide because it will be also linked to the app that we'll present in the end. I already spoiled you. I already gave you spoilers with the architectures, and I hope you're not already checking up your phone. Another thing that happened was the revolution of depth. And this is linked to a lot of stuff. People were trying to build more complex architectures. I'm sure you've observed that here, this architecture is quite simple, but I assure you that AlexNet is more complex, and it was even trained on multiple GPUs. Well, imagine that here on the right, AlexNet is at the bottom and achieves like 60% accuracy, while other architectures that were developed are even more complex. And as you can see, we also have a trade-off between how much time it takes for a neural net to be trained and achieve a certain accuracy. Also, these circles represent the memory footprint that an architecture or a task, let's say, leaves behind. So in time, from that year till present time, everything went deeper. And by deeper, I also want to mention the LLMs that are even huge, are even larger. So what's the solution? Are we going to use an inception model or a VGG for mobile apps? Well, not. We also have mobile nets. The mobile nets are a concept or a dream that we still have. It was first introduced by a Google team, and what they are efficient convolutional neural networks designed for mobile and embedded vision applications. And some applications that we can have with them are object detection, face attributes, remember the previous slide, fine-grained classification, landmark recognition, and many other applications. What they are, the mobile nets, they are lightweight architectures that come to help us to not compromise the performance. And I want to give you like the technical insight mobile nets. They are compared with the standard convolution, which does on the left a channel-wise and spatial-wise computation in one single step. As you can see, we have here an output, while the mobile nets introduce a depth-wise separable convolution. I know it's a complex term, but it's not quite complex. We split this concept in two. We have first the depth-wise step, which does a single convolutional filter for each input channel. This is it. From this cube here, we extract here the depth-wise convolutional filter. And furthermore, in the second step, we create a linear combination of the output of depth-wise convolution. And we arrive to the same result compared to the standard convolution. And we have the architecture, let's say, the architecture inside. We have the A domain, we have the convolution, the convolutions, let's say. Now, I want to introduce the transformers concept. Why? Because it's linked to what happens today. And I also want to talk about the NLP domain. The NLP comes from natural language processing. It's a subfield of machine learning, let's say, in which we are treating text. And if we've seen that the advances in the I domain were done in vision, in computer vision, that was because we are able to parallelize the computations that we are doing by using the convolutions, which are basically matrix multiplications, as you've seen here in this figure. Imagine that we are going on this square, let's say, from left to right, and we apply multiple times the convolutions. We can parallelize this, but in language, what we have, what's our input data? We have sequential data, which involves sequential processing, right? And here in language, order matters. So the NLP progress, let's say, it was slower. And we have here another architecture because, again, we want to represent what's happening. And this LSTM, because it's an LSTM cell, brings the concept of memory, which is, again, very nice. It's also linked to us humans. If before in the previous chapter we had the vision, the eyes that are helping us to learn about the environment, here we have the concept of memory. And what's the principle was the underlying principle of this architecture? Well, they wanted to overcome what it's called vanishing gradient. And wanted to allow the model to capture and learn long-term dependencies from sequential data. And if you are not familiar with the vanishing gradient problem, well, imagine that when we are doing the learning procedure, you cannot further learn because your gradients become very, very small. So you cannot backpropagate the information. And to give you another small insight about how this schema works and why I love them, here you are learning an error. You try to minimize the error. You see how my slides are linked? And that's why I hope you are still here. So coming back, their contribution was this memory cell represented in green that contains some gates, multiple gates, that were used to regulate the information flow. They had an input, forget, and output gates. These are somehow represented over here. And what they do, they make a decision. Do you remember I said that we want to make decisions? So they select and retain some information over the long sequences. And some tasks that were proving their usability are the speech recognition, the language modeling, time series prediction, and many other tasks. So coming back, these are some memory cells with gated mechanism. They regulate the information flow and control it over some very, very large extended sequences. But how large, how deep? Well, at some point, they are not, they cannot be used. We cannot use very, very deep LSTM networks, and for sure for not very long sequential data. And I also want to mention that the GPUs were not used at their true potential, because again, the computations were done sequentially. So that was, again, somehow motivation and an improvement. We have improvement, the concept of memory, and the motivation to come with the transformers. But before arriving to transformers, we also have the concept of attention, published in this third paper. Here, it was in this paper, it was bring the idea of attention. How? When we are doing a task in NLP, which is text translation, right? I said before, speech recognition, we have another task, machine translation, language translation, how do you want to call it? What we want to do is to come from this input English data, let's say, to a French output. As you can see in this figure, for let's say translating European Economic Area, we have la zone économique européenne, right? And what the researcher did, they said we should look at all the other words, not to the exactly that word, like economic cannot be mapped just to economic, right? Why? Because in translation, or in this language task, the order of words, it's different. Not all the languages have the same order, right? But we have, again, a concept. We have the idea of context. I want to insist over this concept, over this word idea. It was an idea, and it was built upon RNNs. So what's again RNNs? They are recurrent neural networks. They are processing the sequences as I said, sequences sequentially. Some other examples that I also like. As you can see, we can have SVP, s'il vous plaît, or veuillez ne pas toucher. Usually in museums, you see this. Just to give you an intuition that we don't have the same order, we don't have the same mapping, one mapping. We have to look around. We are not looking just straight, right? And what about these languages that use signs? Here we have the Latin alphabet, right? We still can have an intuition about these words. Hopefully, the transformers were also built, and this is a very important paper. The attention is all we need, right? This is the foundational paper that is actually at the core of everything right now. Everything that is awesome and you like it, from image generation to homework generation, you know. But to understand, of course, the paper, we go directly to the schema of the paper. And I know it can be scary, but don't worry. I split it in multiple steps to show you how awesome it is to look at the paper, to use it, and further develop it, because that's how AI domain evolves. So, breaking it, first component of the transformer is the encoder, is this wonderful pink area which processes the input sequence and extracts meaningful representations. And what they did after each layer, remember that we need multiple layers. We are not using just a perceptron. We are performing a normalization step and some residual connections. As you can see, we have some flashes over here. These are the residual connections. And what they do, they solve all our problems related to, of course, vanishing gradients. If we have an encoder, we also have a decoder, right? We have input, output. What the decoder does, well, it generates the output sequence based on some observations learned by the encoder, and also based on the previously generated tokens. This gives us another interesting behavior. It's autoregressive, right? We talked about encoder and the decoder. Now let's go even deeper. We have the self-attention right here at the core of the encoder. And simplifying everything, here we can see how for a single word, here the making word, we can learn the dependencies of this word with the other's word. How? Well, each input token, because we agree, each input token, a word is a token, can look, or scientifically called attend, it can attend all the other tokens directly. And that's how the magic happens. That's how we capture efficiently the so-called long-range dependencies. And voila, that's how the context is built. You remember that in the past we had the idea of context. Now we have the context itself finally built, and I will show you how simple it can be built if we look at the map. But before that, I want to give you an example why the context it's also important, besides the order of the words, of course. If we have the sentence, time flies like an arrow, what it means? What's the meaning of the word flies? It's like a first question at the Romanian exam. It passes very fast. But when we say fruit flies like a banana, we have another meaning. The mosquito, let's say, like the banana. So that's why it's very important to have a context, right? Even for us humans, we need the context to understand what's happening with our life, with our studies, everything. It might be scary. I don't know how you feel about this concept, but I wanted to show you how simple it's to have this self-attention. It's all about the scaled product attention. Why it's scaled? Very simple. We have a normalization over here, but we have also this mathematical attention formulation, which has again three components. The first one marked here in pink is the query Q, which at the very intuitive level represents the information we are interested in, the information for which we do a search. And our very dear friends are, of course, the cats once again. So let's say we want to search about what are some interesting facts about cats. Well, that's our query. And to look at the math, this is just a query vector. What we are looking for and what we are trying to understand from our input text. Going further, the keys of self-attention from this formulation help us to identify the relevant query-related info. This can be very simple, like an index or identifier attribute, like purpur, felino, kitten, right? So it's the relevant query-related info. Again, looking at the math, we have a key vector. So it's representing the relevant information in the input text. Finally, the values from the math represent the content answering to the question, the content. We perform a search and we retrieve a content like this one from Britannica, which brings us a description related to cats' behavior, their characteristics, right? This is a value vector and is the current information from content that is associated with the keys. Of course, I don't want to make everything harder. We have also a softmax function applied to this very nice math formulation, but I wanted to show you how the scaled product attention goes to the multi-head attention that you remember was in the beginning of our architecture. These are just multiple scaled product attentions captured with a search and depth from here. And you see here the heroes of our lecture today, Q, key, V. We also have the concept of cross attention, which is here in the decoder. This combines two different embedding sequences It's just a technicality that they must have the same shape, but they can be different. And this is very, very interesting because we can combine images with text, the text with sound, the sound with images, as you want to, as creative as you want to permute this. It's important to know also that one of the sequences, if we have two sequences, one of them will play the role of Q, and the other we produce the KV pairs. And what are some tasks that can employ this type of cross attention? These are image text classification tasks, the next token prediction, or again machine translation, right? We also have another component here, the positional encoding. Remember that we have sequential data, we have words, we have to keep in mind the order of words, right? And for this specific problem was employed the positional encoding. Why? Because we want to integrate our order into the representation of words, and of course provide information about the position of tokens in the sequence. And that's how, my dears, we can parallelize the computation and process all the tokens once. And that was with the transformer. It's a very important concept. And now let's dive into LLMs by presenting BERT. BERT, this abbreviation from here, comes from bidirectional encoder representations from transformers. As you can see, we have some concept idea developed by a certain group of researchers, which was furthermore taken by others, and a third, let's say, group of researchers developed it. So you see how there's a chain of evolution, right? By looking at the name, previously we have attention is all we need. Here we have the bidirectional keyword. Is the first word. And why it's important, why it's in pink? Because it gives the idea concept of left-right context. By having bidirectional encoder representations, we can have very deep contextual relationships. And how we arrive to this? Of course, using multiple data sets. If in Vision we had ImageNet, let's say, but of course other data sets. Also in language, we need data sets, right, to perform the evaluation, to see how this machine or this ML model is relevant on some language task compared with a human, of course. So their first contribution was to evaluate or put the problem on multiple data sets. These are some relevant data sets. They also came up with a very interesting idea, the idea of mask sentence, mask language model. Again, using our intuition, when we are masking some tokens or some sentences, we are forcing our model to remember other concepts, or we are forcing it to learn even harder. By masking, it's the same intuition. And we also have some sentences in this schema, sentence A, sentence B. This concept contributes to the next sentence prediction task. What it means? Very simple. This can tell us if two sentences are successive or not. And that's how we have a relationship between sentences. And this even further comes with the task question answering, right? We have a question, how is the weather today? We have also an answer. It's very hot out there. It's cold. I don't know, right? What are the applications of transformers? Some of them, because of course there are daily. We are developing daily new applications, new solutions. You are going to develop your own solution, your own application. I already presented the LLM, starting with BERT. I want you to tell you that the T from ChatGPT comes from transformers. We can make musical composition. We have the AlphaFold. We can generate images. That's wonderful. So the 5th chapter. So far we've seen computer vision on its own. We've seen somehow an idea of what the language does in the A domain. What are some relevant concepts? What if we want to connect the text and the images? This concept, or this task, as you want to call it, was introduced by Clip. It's also an architecture that I want to present to you to see how beautiful we can link the vision and the language. But before that, I want to introduce another concept that I really like. It's the transfer learning concept. You are going to also use it in your mobile app, and I will explain you later how or why. And what it means. It means that we are reusing the knowledge learned from a previous task for a new task, but in a different field. Ideally, we have some data for both the training and the evaluation phases that have some distribution that is similar. It's a very often recurrent problem that the domain of the evaluation data can change over time, right? And we might have also some data that is enough for a task that we can use it on a similar domain. When talking about transfer learning, we can also have a risk. This risk is the negative information transfer, in which our domains, from which the domain from which we want to use the information, transfer the information, transfer the learning, are non-tangential. Like, if you remember my schema, imagine like AI. It's non-tangential with melee, but this is a false affirmation, right? So we can have negative information transfer, and you also should have in mind this idea. But again, let's see at an intuitive level what transfer learning can mean. So let's say you are a person that's doing boxing, but at some point you want to change to body combat, right? You want to become a specialist in body combat. These domains, both boxing and body combat, they are tangential, right? Because they come from a bigger domain, from sports. And first step is the knowledge transfer. With what we are going to transfer? Well, we are going to transfer the jabs, crosses, hooks, uppercuts. These are punches. We are also, and these are common, right? We are also going to transfer some skills of head movement, the footwork, our defensive tactics, right? We somehow have developed, while doing boxing, a sense of time, rhythm, and distance, right? Now let's reuse our pre-trained skills. So what we are going to reuse, as I said before, the kicking techniques, the agility of footwork that we want to adapt, and the defensive techniques, blocking, of course. Lastly, and most magical step, fine-tuning, adaptation. That's exactly what you are going to do for your application, for your mobile application. We are going to fine-tune, another keyword from today's lecture. So here we are adapting our specific kicking techniques. We have some specific techniques that we want to learn and adapt. Those are front kicks, roundhouse kicks, side kicks. These are new skills that we want to learn and adapt in our new domain, which is the body combat. Also, we have some elbow and knee kicks, and also we want to adapt to our cardiovascular endurance. It's faster. Body combat is faster compared to boxing. Now, why I gave this example? Because a common practice in the AI domain, or let's say melee engineering to be more specific domain, is to take a certain architecture. Let's say you take a LeNet or AlexNet or MobileNet, and these architectures were already trained on large corpuses of data, like BERT. BERT was already trained on 3 or even more data sets of languages. So these architectures already exist. They are already capable to recognize some task. They are already capable to perform well on some task. Let's say that we take LeNet. It was already trained on MNIST dataset. MNIST is with handwritten characters. You can adapt it to some other task that is also tangential with your task. Other example, you have an architecture trained on ImageNet. It can classify 1 million objects. Maybe you want to detect food, right? Classify food. You are going to adapt your architecture to your new task. And that's when you are going to do the transfer learning. Another concept that I also want to introduce before talking about CLIP, that was the purpose. The purpose again of N-shot learning is to learn from a limited label data. That's interesting, right? So we have a lot of data, but now we want to learn from limited label data. N-shot learning. N refers to the number of label examples that are available per class for training. And it's usually a small number, 1, 5, 10. It's not infinite. And why it's important? What was the reason for which we are going to use N-shot learning? Because having a lot of data to retrain, to reannotate, it's costly, it's time consuming, it's not practical. Also, we want to generalize. We want to be able to have architectures or models or applications that can be easily taken from one task to another. And we also have some new techniques that are developed, the meta-learning techniques. These are basically used to capture the patterns and similarities per task. And what's the quintessence of N-shot learning? It relies on information and connections learned from a large number of examples from many other classes. So, reformulated, we have very, very large connections in the data, and simply put, we make connections and we are going to transfer them, right? Very nice example that I also like. And it came up to my mind when I was thinking about zero-shot learning. What zero-shot learning first means, it means that we are going to recognize and classify new examples whose classes have not been seen during training, but for which we are going to use additional information. Simply put, if we are going to visit prion.com, we are going to meet DALL-E Mini. It's mini, right? It's a small model of image generation. And what we are doing there, we are giving it some additional information, a prompt, an avocado armchair. It will be really nice to have an avocado armchair in our house. And imagine that during training, this model didn't see like an avocado armchair, but it was capable to generate images with avocado armchairs. It's interesting to notice that when we run multiple times, here on the left we have the first attempt of running, second attempt of running to the right, we have different outputs. And this is an example of what zero-shot learning means. One-shot learning is very simple. We have a simple query, an image, in this case with this cute animal. That's the single labeled example of the class. And this time during the training, we can make a prediction that the similarity between my query, this cute animal from here, is predicted with a 0.9 accuracy. It's somehow linked to the rabbit or hamster, but it's not that close. Few-shot learning. A few label examples of the class. So while training our model, let's say we have an object detection model. We have seen some animals during training. There are multiple query images. And now in the wild, and this is another keyword, in the wild, literally, we are able to make predictions about other similar objects. But these are not objects, are animals, of course. And we've talked about transfer learning and shot learning. It's time to to put everything together and introduce CLIP, which is a contrastive language image pre-training model, which relies again from its name on contrastive learning. This means that we want to maximize the similarity that we have between similar pairs and minimize the similarity between dissimilar pairs. Does it make any sense? When we have some pairs, those that are similar the pairs that are similar, we want to make them stick together, and those that are not similar, push them further away. And CLIP was trained on 400 pairs of images from the internet and their associated descriptions, like titles and labels. The data was also diverse and noisy. And this is a very interesting idea because we have pairs of images and descriptions. Do you remember that when chapter 5 arrived, I said connecting text and images? That's how we connect them. We have pairs. For each input image, we have a description. Like, let's say an Instagram photo with a caption. It's quite relevant as an example, intuitive example. What's our task? We want to predict the pairwise description for an image from a very large pool of randomly sampled descriptions. So we want to predict the pairwise description. Our intuition tells us that we learned some visual concepts from images, and we associate to those visual concepts a corresponding meaning or name or caption in natural language. That's how, again, at an intuitive level, we are connecting images and text. Coming back to math, I hope you like it. It's quite simple again. As I said, we want to compute somehow a type of similarity. And we have the word lion and an image. In this case, I took the liberty to use Emojipedia. The image of a lion. What we are going to do is to compute this cosine similarity between these two vectors, where in a common representation space for both images and text. This common representation space, it's a space in which we are putting the embeddings, meaning, let's say, intuitive level vectors that are representing the features of visual concepts together with the text. And this is where we want to bring together those vectors that are that do a match, right? And we are doing just a scalar product of the two representations. So we've seen the math, we've seen the theory. Now let's dive into the code. That's all we want. The pseudocode shows us that we have an image encoder. Let's say it's a ResNet. It can be any other relevant architecture. A more powerful, a vision transformer, or anything more evolved that has at its core a vision, a transformer. That's exactly why I introduced this concept before. We have also a text encoder. Each one of these two pieces is used to extract the feature representations, right? We have an architecture that processes the images and an architecture that processes the text. And we are going to do some joint multimodal embedding, for which we compute the pairwise cosine similarity because we are respecting the math. And of course, we have here the laws, which is a relevant laws that helps us to do the learning. We also have to learn. We are not just putting their pieces and forget about them, right? How it looks like, the pre-training, the contrastive pre-training. Again, a schema. We have the image encoder. This time we are going to use cats image. Oh, sorry. I wanted to say this time we left behind the cats and we are going to use the dogs. So we have some images with dogs and other animals, of course. We pass the input images, the input images to an image encoder. And also, on the other hand, we have some descriptions about the image. Pepper the OCPUP. In a matrix, we are going to merge together the embeddings of images and text. And what we want to do is to maximize this principal diagonal, right? We want, and this intuition from this figure, from this architecture, represents exactly the theory that I presented before, the contrastive learning, the contrastive pre-training. So we want to maximize the similarity between these two pairs. And we are going to do this for any other examples, right? Not just the dogs, also other objects. And let's say we've done the pre-training, right? That was the first step. Now we are going to create a data set that is adapted to our, in this example, classification task, right? It's a classification task. We want to classify some objects. And let's say we have 10 classes. We have plane, car, dog, etc., bird. What the researchers used a technique that I will explain further. A photo of an object. Here, the object, let's say the object keyword shows us where our class, let's say plane, will come, car. We are going to use the keyword object with our desired label that we want to predict. Here, after putting this together, we are going to pass to the text encoder once again exactly what we want to classify, and we are going to combine this data set for classification for zero-shot prediction. That's why I introduced before the n-shot learning, the zero-shot learning. Here we have zero-shot prediction. What it means that I'm going to give unseen images because we don't want to overfit. We want to generalize. We don't want to memorize images from this world, right? And what we want to do in the end, we want to do that perfect match between my description, my input image, with a generated description, a photo of a dog, right? And that's it. That's how we link the images with the text. Well, let's talk about performance. Performance is something also very, very important. that you will also want to achieve in your mobile apps. You want to have good performance, right? As you can see, on the right we have a clip. Vital, it's just a version of the clip architecture. L comes from large. We also have another architecture, ResNet, and on ImageNet, which was the origin of everything, this clip achieves exactly the same performance as ResNet, but its magical happens here further on ImageNet Sketch or ImageNet Adversarial, which are data sets where some images from ImageNet were somehow represented differently. And by differently, I mean these examples, these visual examples. Again, we have some bananas. I hope you like fruits also. So in ImageNet, it's pretty clear how bananas looks like, right? The delta score means the improvement that clip has above ResNet. No improvement. But here in ImageNet Sketch or any other more complex data sets, this is really cute ImageNet Air, some puppies of bananas. We have an impressive performance, right? So clip was capable to generalize even better than ResNet on images that are even more complex than ImageNet. And to summarize the issues that were addressed by clip, first, the cost of data collection for ImageNet, 21K. There are even other versions of ImageNet. Look at these numbers. How many people, how many tagged images, how many classes were collected. Clip just learns from text-image pairs that already exist on the internet. Again, the internet plays a crucial role for data collection. The narrow models is another issue. Why? Because to reuse a model trained on ImageNet, just ImageNet 1K requires some modification to the network, some new data collection, and of course fine-tuning. Why we are doing this? Again, to transfer our learning, to adapt to a new task suitable for our use case, right? Clip only needs natural language descriptions of the new concepts. And another issue, it's a very huge discrepancy between the results that a model can do on a benchmark and in the wild. Do you remember that when I had that slide with object detection, I said in the wild, it's also a very important keyword. You don't want your architecture to remain in a research paper and be optimal just for a benchmark. A benchmark, it's some sort of data set that it also includes metrics like here. You don't want to have a model that optimizes just for it's optimal just for ImageNet. You want a model that is capable to recognize your class no matter how complex it is, right? You want to predict bananas no matter what shape bananas have, right? And this is a very important issue. You want your application, you want your problem to be relevant for this word. Some examples that come from clip paper. As you can see here, we have again some input images for which we make description. What is here, right? You pass an image to ChatGPT and you tell him, describe this image. Clip says a photo of an airplane. Similar for annual cropland television studio. We also have here for guacamole some sort of technicality for generating descriptions. You remember I said before, here when we create our data set, we say a photo of an object, but here our model can say a photo of guacamole, which is a type of food, right? So we encapsulate, we make a link between what is guacamole and its hyper domain, which is food. Some very, very nice and useful application from health. What is kind of sad is probably this Street View house numbers application. It's not so capable to predict numbers. And I will talk about the trade-off between plus and minuses of clip, but let's look at the efficiency, performance, as you want to tackle it. So just a detail, the contrastive learning is more efficient than just making image to text prediction. And they discovered that the vision transformer brings more efficient solutions than using a ResNet. And what are the limitations? Some images that were not seen during pre-training are not so well predicted. This leaves us to poor generalizations. When talking about abstract tasks, such as counting, there are issues, you've seen it before. If we have very specific tasks, such as classification of flower species or something very, very specific, like a student that needs to make predictions for a PhD course, it's not so easy. And again, some complex tasks like distance estimation bring clip to limitations. We also have to keep in mind when we use a model or make an applications that what are my limitations? I have to see my blind spot. Why? Because that's how I learn. I learn from my mistakes. I learn from failures. That's how I can bring new ideas, right? Like we've seen in the past with the concept of memory. What were the limitations? Well, I'm learning from my limitations and see how can I improve them, right? That's how the transformers architecture was invented. Clip also came with the prompt engineering concept. I'm sure you are also familiar with prompt engineering. So Clip did it before ChatGPT was cool. And why we're talking about it? Because in language, we have also the polysemy issue, which means that we have many possible meanings for a word or phrase, you know. Clip or in general, the language tasks are very sensitive to the phrasing of descriptions. Yeah, that's a very interesting example. The prompt engineering, as I said, it's sensitive. The researchers discovered that when providing the labels for the text encoder, if we are going to use that schema that I showed you before, a photo of a dog, a photo of an object, or a photo of a label type of another domain. We have the content, the context. We have more context for our image. We can generate multiple descriptions with more meaning. And this help us to the generalization, to achieve generalization, right? So the prompt engineering industry, it's also important because you want to have in mind, how am I going to build my classifier data set? You want to have some sort of context over here and generate accurate descriptions. So I think so far we talked about vision, language, connecting them, but it was also a very important issue on the first slides. We want to have some small models that we can use on our mobiles and also make accurate predictions no matter the task. And this is where the quantization theory comes in place. Because we have a trade-off. We have these models, ResNet, I mentioned it. It comes from Vision Transformer. We are familiar with it. Other versions of it. Remember the memory footprint, and we want to have a very, very, very good prediction, which is measured by the accuracy compared to the model size. And on the right, we have the mobile net versions, which are achieving like 10% lower accuracy. And this is where the quantization comes in place. And it's very important because it shows us some techniques that allow us to obtain a smaller model. I would say it's a black box, our model, but let's keep it as a gray box from our original model. We want to make the models accessible while models are getting bigger and bigger. Why? Because we want to do scalable and efficient AI model inference, right? We want to make a compression. But how? First technique, it's pruning. It means that we are going to eliminate some layers within a model that don't significantly influence the model's decision-making process. And from these layers, we are going to prune some synapses or neurons. As you can see, we have, let's say, a representative schema before pruning. We arrive to a more clean and sparse schema after pruning. That was the pruning. We also have knowledge distillation. It's another concept that helps to the model compression task that I also like. Why? Because it's also linked to our reality. We have two models, a teacher model, which is bigger, right? And a student model. And during our training, our target compressed model, which is the student, uses the output from the teacher model, which is an instructor, right? So again, we have some big model that learned on a lot of data during a lot of time on some powerful machines, and we want to to transfer the relevant learning for our task. And that's how, at a very intuitive level, we are going to do knowledge distillation. Now the quantization. What it means, quantization? It means that we are going to store the parameters of the model in a lower precision. This means storing in a lower precision, that we can quantize the weights, the W's. Remember from our perception that we have some weights. Also the activations, which are the values that propagate through the layers of the neural network. Remember that we had some signal that was firing up or not our neuron, and in this case, our neurons. But what's about these lower precision parameters? We have to talk about the data types, right? In general, we have some values that are stored in FP32 space. They look like this. They occupy, like for this simple 3x3 matrix, 3 bytes to store each value, plus 4x8 byte precision, because we want also to be precise, right? So in total, we arrive to having 36 bytes. And as I said, by doing quantization, we want to store the parameters in a lower precision. Lower precision, just to give you another example, there are other types of lower precision, but let's say our target is int 8. This will give us just 1 byte to store each value, plus 1/8 by precision, we arrive to 9 bytes. So we decreased 4 times. Amazing, right? Do you think this happened without any cost? No, it always comes with a cost. This is the error, more precisely the quantization error. What we want to do is to lower this error as much as possible without compromising the performance degradation. The thing is, the fewer bytes we possess, the less accurate the approximation will become. And on pink, again, I represented the quantization error that comes from this process of converting just a simple 3x3 FP32 matrix to int 8. The error by just looking at it is not so big, but it comes with a cost, right? There's also this concept of linear quantization, which means that we want to map the floating point range, R min, R max, to the quantized range, Q min, Q max. And how we are going to do this? In Python, I took the liberty to pick Python as my language of preference. We are going to simply define some floating point values. Again, here we are talking about dummy float values, right? We are not in a real scenario. We are going to define the quantization range, which can be, let's say, -1, 1. We want to do a quantization, the quantization in this -1, 1 range. And how we are going to do how we are going to obtain the quantized values, we are going just to apply, again, some math that is not that hard, that allows us to obtain the int 8 values. So after running these simple lines of code, I obtained these quantized values. You are familiar already with the quantization error. As you can see, this time it's the error is somehow smaller. But I also want to tell you that we also have a concept, which is dequantized values. What if I want to come back, right? What if I want to come back to the original values? Well, sometimes we can do this, and it's very simple. Again, I'm giving you these techniques of computing the dequantized values. I used Python as a starting point on how can we compress the values that we have. But for AI domain and using let's say the architectures that I talked about earlier, we need some frameworks that I will introduce later. And one of them is PyTorch. So in PyTorch, we already have a pre-trained quantized MobileNet V2. Amazing, right? And I want to show you that here we don't need to do this math applied to code by hand. We have some simple functions that are quantization. Also, I will show you later. But here, as I said, we already have the pre-trained quantized model. We have the model quantized, which is pre-trained V2, quantized true. We are just passing the flag, right? And we also can load the original model, MobileNet V2. If we want to compare the size, right, we notice that the original model has 14 megabytes and the quantized model has 3.6 megabytes. So we have almost 75% decreased. Finally, the mobiles. Let's say we have this Hello World application that is also available in PyTorch. And now I want to present to you a functional demo. What is happening here? First, let's define the task. We have an image, a query image, and in the Hello World app, we have, if everything goes right, a predicted label, which is a white wolf or article of, it goes even complex, the name in Latin. How is this possible? As you are in a mobile, let's say you are in your Android Studio already installed software, everything goes right. Well, in the assets folder, you can put there your model. In this case, let's say it's a MobileNet V2 quantized, and your target image. This is the image, right? I said before that I used PyTorch. What if I want from my Hello World application to infer new images? What I'm going to do? Well, it's very simple. I have to modify this main activity Java file. How? I'm going to change the image, I'm going to change the model and rebuild the application. And on my running device, my emulator or your real mobile phone, I'm going to see my predictions, right? A very nice image. I was wondering if this model is capable to predict something about our university, right? I hope this image is familiar to you. Unfortunately, it predicts a streetcar, a tram, a trolley car, and I wondered why is this happening. Well, the thing is, the image it's very far away, of course, and it's not specialized on predicting some universities that look like this. The proof is right here. It's amazing to see how our university has an architecture that reminds of a palace, right? Very funny. Even more, I wanted to see if I'm introducing a car, because before I saw a streetcar, tram car. I was wondering if the model will focus on recognizing cars with a weight bigger than the building's weight, and in this case it didn't happen. Yeah, so why I'm giving you this chain of thought, not because I want to talk about my chain of thought or about me. I want to talk about how am I going to test this application, right? Well, it's kind of time consuming, right? To insert here thousands of images and see what happens. It's a building, it's not a building, it's some sort of person, some sort of machine. I think for your application, I'm giving you my intuition, you should somehow automate, first of all, automate this step of inserting images in assets folder if you are going to use this demo, Hello World demo, or others, because I will also present others. So first, you have to come with something smarter for retrieving the images. And second step, which is also very important, before deploying your application to see how it performs on mobiles, it will be smarter to test it locally, like to see from your data set, your evaluation data set, which should be somehow tangential with the training data set, right? You should see how it performs. It's your prediction accurate or not? If it is, with which error? You see, we are putting together all the concepts. Like if your purpose, let's say, is to detect buildings in your university campus, well, you should somehow adapt this model, because from what I've seen here, it doesn't perform so well. Like, okay, we can say that we are going to the palace, but it's not the palace, it's the university, right? So these are two steps that should be very clear to you, should be your scope, your task. You want to automate this retrieving image process, and second, test your model before deploying it, because for each image here you have to rebuild. This is just the Hello World, and is very, very useful for everything. But we also have some other applications that are more complex, like this one for detecting handwritten digits. It's very interesting that now we have the MNIST dataset, and it's bit for MNIST. Transformer. And let's see a short demo, how it should look like. Yeah, I took also the liberty to deploy it on Android. So a person draws the symbol of 2, and it's very simple and intuitive. The user, it's somehow supposed to click on recognize, and we see that it works. It recognizes 661, so it goes even further. The last chapter, the know-how, this is the end of the presentation and practically the start of your work. So I already did the disclaimer of tools, but being more specific, you should select the mobile ecosystem considering your technical preferences and expertise. You have two options. You can use the TensorFlow Lite ecosystem or the PyTorch mobile ecosystem. It's up to you. Maybe if you are pro Meta or pro Google, but I would say just consider your technical preferences. And if you click on this underlined text, you will end up in their documentation, which is very, very good. I've seen students that are just using this documentation and they are building their applications based on it. If you are or if you did your decision, you said I'm going with TensorFlow or I'm going with PyTorch, you should align this ecosystem with your ML model, because what you want to do is to optimize it for your application to be performant and efficient. And the first step that is available also for TensorFlow is the same thinking process, right? You are going to transfer this knowledge to TensorFlow if you want to use TensorFlow. The first step and the most important step, which makes the difference between a successful project and a work in progress project, is to start simple, is to perform the technical configuration. And I will insist on this from start till finish. So you are going to go to PyTorch Mobile or TensorFlow Lite documentation, which tells you step by step how to do the setup. And I really mean it, if the errors persist, so do you, right? No matter how long it takes to you. Of course, not till you arrive to your 60s, but you should pass through the error, right? You want to keep your scope alive. And let's say you solve the first step. You started simple and you did the technical configuration, and let's say your Hello World app works from start till finish. Like you can see the wolf prediction. Now you start doing your stuff. That's the step in which you start thinking about your problem even more. So what you can do here, you can utilize a ready-made solution. a machine learning driven solution, which is available for common scenarios, right? What are the common scenarios? Well, some tasks are the question answering task that for which you already have, let's say, a theory behind you, right? You have seen the BERT, you have seen the transformer architecture. Here, as you can see, you have some input text and the query, and you want to predict the answer. You want to provide the answer, actually. Here it tells you some info about PyTorch Mobile. Maybe you are a fan of vision, of computer vision. You can do image segmentation, which is basically classifying pixels in an image. As you can see here, we can tell this is a person and this is on blue, this is animal class. Or maybe you want to do object detection, like identifying in a box the classes. We see here person, a horse, other horses. My advice will be, you already have quantized models, no matter the library, already made solutions. This would be great if, in this step, it would be great if you will be creative, in a sense that you can combine multiple machine learning areas. We've seen computer vision, we've seen NLP, we have a sense of how can we combine images and text. I didn't mention the reinforcement learning area. This is also very nice because maybe some of you are familiar with the games. In games, we have images, right? We have also the agents that learn based on some policies how to perform some actions, right? So what if I'm just suggesting to you, you will find a way to combine these areas by starting from your technical setup and combining already trained ML models. That was one side of suggestion. You should have in mind that you can use, as I said, a pre-trained model, but you should check if your model, of course, matches the use case. Like, you have to have in mind what's your app about, also how it will look like you have the space to put over there everything that you want to do, like you want to segment, you want to do object detection, you want your segmented person to play football, what do you want to do? So you want to see if it matches the use case, like what's your problem, why even you are bothering to do this. Also, you should keep in mind always, and these 2 and 3 points are very linked, the optimization level and how the degradation of performance affects, what happens with the performance. Always test, I would suggest again, test before doing the deploy. Of course, test during the deploy, it's obviously, but what happens if I'm using a very optimized model? Another option, if you are going to utilize a ready-made solution, is to adapt an existing model, right? You are going to retrain the backbone across a custom dataset, as I said before, but here we are just doing in PyTorch Mobile. A third step, which is not it's not demandatory, but it will be nice, you can build also custom model. You can build your own custom model and quantize it for deployment. Again, it depends on your expertise and your use case. And I think we arrived to our resources. Yeah, those are some of my resources. Let me know what you think about it, and if you have some questions, and I know how to answer them, let me know. And I'm impressed that it's I don't know when the time passed. It's 12 o'clock. Yeah, actually, I don't know why this slide didn't show up, but I want to also show you this GIF of Visual Transformer. As I don't know, it didn't play it. It's very nice. So here for Visual Transformer architecture, we have some input image, which is patchified. These are some patches, and they are projected in a flattened space to which we add some class embeddings, and that's how we are going to do some predictions using a MLAP head. This is just a detail because I mentioned so often bit, but I don't know why it didn't show up. That's it. Are you still here?
Yes, we are here.
I hope I covered everything. Like,
I hope, yes, you covered everything. I hope it is considered useful by our participants also. Thank you, Alexandra. I will tell them if they have questions. Maybe they watch again the video and so on. If they have questions, they can send me and I will transmit to you the questions, and maybe you help us with some answers.
yeah, it will be great. Yeah, it's useful, like taking the time to reflect upon everything and ask questions. Yeah.
Thank you very much for your contribution to our hackathon, and I wish everybody a nice Saturday. Goodbye.
Thank you so much. Bye-bye.
Thank you. Goodbye.